All right, so let's talk about simplifying trig identities just a little bit and talk about some general strategies and how to do it. Okay. Equations and expressions. There are actually more tools that I would use, more strategies that I would say are for equations than for expressions, because you know what your target is, and you can sometimes say to yourself, all right, what do I have to do in order to get to my target? Whereas with an expression, you don't necessarily know what your target is. You're just going for the most simplified, okay, whatever that looks like. So for example, I would say common denominators is one. Look for things that you can add or subtract if they have fractional forms. Think about common denominators, like if you have a tangent, if you have a cotangent, a secant, cosecant, things like that, which are naturally a fraction or can be turned into a simple fraction. Look for those. Look for GCDs. GCFs, greatest common divisors. A divisor is a factor; they're the same. So look for those. When you have things that are squared, okay, then those are usually targets to go to. If you have things that are not squared, then it's kind of harder to turn it into something simpler. Okay, so generally I look for the thing that is the most complicated looking. Okay, the thing that has the most fangs and horns, kind of thing. So, and there are ones that we'll see that have something cubed or something to the fourth or whatever, stuff like that. Later on, when we learn a couple of more tools, look for double angles or added angles. So for example, the cosine of 2x, something like that. Because there are trig simplification rules for multiple angles. So added, and this is for later, but okay. We haven't gone there yet, but we will very soon. We'll be doing that next week. But I want this list to be useful to you not just now, but later on. Okay? Because there are, like I said, there are identities for those. We'll come back to this list because there's one that I think is very important, and this is specifically for equations. And it's my, it's kind of a weird little process that I call using a trail of breadcrumbs. Okay, familiar with the story of Hansel and Gretel? Okay. The concept behind it is you head out on a path to try and here's where we got. We got location, we have home, destination. Okay. We have something that we are starting with, and we want to turn it into something else. Okay? A start and a finish. Well, you can go as far as possible towards your destination and then hit a brick wall. and have no idea what the heck to do from there. You're stuck. This isn't just for trig equations, but this is true for most problem solving, okay? Especially if you know what your answer is, okay? And the question is, get me there. Find a path to it. Well, you go as far as you can, you hit a brick wall. And what you do is you look at your solution and you say, what can I do to turn my solution into the original question? In a sense, go backward, right? And follow, find some way to turn your solution, work your solution as far as you can, and hope that somewhere in the middle of the forest, separating the two, the beginning and the end, you find a common thing. You can say, well, I can turn home into this point A, and I can turn my solution into that same point. Well, then all you really have to do is write it in reverse. In a sense, you've found the same point in the middle of the forest, going from both directions. You just follow the path home. And we'll use this later on down the road. All right. So this technique of using a trail of breadcrumbs we'll investigate thoroughly, because some of the hardest problems that you'll solve can be taken apart by using the trail of breadcrumbs technique. All right. Okay, so I want to just do a couple and see what happens when we do just a handful of more expressions, okay? By the way, for those of you who haven't yet completed the assignment, are there any in there that look particularly nasty that you want to talk about? Maybe you've worked on them and you can't get anywhere, or maybe you've said, I'm a little bit nervous about that one. Anyone in particular? Anyone look worse than the others? Can you write it out for me? You have it handy? Yeah, can you just read it out? Secant, what?
So that is not the last one. The last part is tangent squared x.
Okay. Okay. Well, we have an identity that allows us to work with 1 plus tangent, right? Okay. I would use that. And then I would think about turning tangents into sines and cosines. Remember, one of the tools when you're looking at this and you're like, well, what am I supposed to do? My first instinct, and it holds for 97% of all of these, is to decompose everybody into sines and cosines. Okay? If you break it all down to sines and cosines as your very first step, you're well on your way to solving it. Okay? Because it's a lot easier when you're only dealing with a sine and a cosine than it is to be dealing with secants, cosecants, cotangents, and tangents, and sines and cosines. You see what I mean? You're just boiling everybody down to just two terms rather than 6. You know? Okay. Let's do 1 or 2 just for fun. So what's your first thought? Common denominator, absolutely. Oh, sorry, come on. Hey. So get your common denominator, turn this into a single term rather than something minus something. So that was the first step you thought of, I hope. Okay, so now let's turn it into a single fraction.
You make it cosine is 1 minus sine squared.
1 minus sine squared. Now you see, looking at that, you can say, all right, well, now what the heck am I going to do? Well, my instinct after doing 100,000 of these is to go after the ugliest thing on the page. There's one thing in there that's different, weirder, uglier, whatever, than everybody else, and that's the cosine squared. So let's turn it into something of sine, so that hopefully we can simplify and cancel out and whatever. So what is cosine squared? 1 minus sine squared. Don't know. Is it's getting uglier or easier? We'll see. Sorry. So distribute, combine like terms, and then see what you have. See, so in a sense, you have a bit of a knot that needs to be untied. Okay? And the process of untying a knot sometimes means pulling on one part or pushing on another to try and get it into a form and see where it collapses. So now what do I mean, it certainly looks a lot better than it did, but am I done? No. What can I do? You can make a substitution, but you don't need to. You know, but GCDs, GCFs, whichever you prefer. Yes, I have a GCD in my numerator, and that definitely helps. And there you go. So, you know, this is not always something that is easy to see at first. And, you know, like I said, it's a knot, it's a puzzle. And eventually they will all collapse. Okay, these questions are not generated, meaning that when an author writes a textbook, this section is not like other sections. And I say that because in other sections, you can make a computer program spit out an algebra problem and produce thousands upon thousands of them by simply changing numbers and rearranging things. These kinds of things are not. These kinds of things they're crafted to be a certain kind of puzzle. It's not like you can just throw trig together and hope that it simplifies nicely into a little thing like sine. Okay, and sometimes the way to actually write these problems is to reverse engineer them. You know, to start with sine and then add a 1 plus sine x up into the numerator and denominator, and then kind of work backward that idea of that same concept about using the trail of breadcrumbs. You're going backward from your ending to create something. Okay. that make sense? Hmm. Mm-hmm. Okay. Yeah. Okay. Sure, sure. Where you know what you're exactly where you know what you want it to be with the induction stuff. Yeah, the induction stuff. Where you knew what the K case was and you knew what the K plus one case was. The question was how to get there. So sometimes you had to start by going to the K plus one and saying, how do I get backward? You know, that technique. All right, let's do another one. I love these problems. They're all over the place. They're so much fun. I can absolutely. Of course. All right, I'm definitely gonna step away from this one. I'm gonna pause the Ronco show, and you guys can work on this for a minute or two. Okay, so we kind of had an extended commercial break there, and the process of like I said, there are different ways to get here, but if you decided to turn it into just sines and cosines, that would be it. You get your common denominator, and now at this moment you can do your double rainbow. Okay. And immediately we can cancel something out. Okay, here you might very well hit a brick wall, right? But the thought is, when you're stuck, target the thing that is the quote unquote nastiest, the one that has the highest, in a sense, the highest computational potential. You have more potential to do with sine squared than you do with anybody else, right? Okay, so let's turn sine squared into something. What do we do? What do we turn sine squared into? 1 minus cosine squared. Now what do we do? It's the difference of squares. We can split that guy up now. It is definitely longer, but it's the thing. What you've done is by turning it into sines and cosines, you've kind of like built this house of cards, and then it collapses upon itself. Question. I'm fine with it. Yeah, it's cool. Yeah, you could if you saw sine squared as those two parentheses, I'm fine with that. It's no problem. Right? And now, yeah, you know what? You might be saying to yourself, okay, this is about as simplified as I can go, but there is one more step that you can do. And now you're done. Okay? Hmm. definitely a longer route than the one we took yesterday for the same problem. But sometimes you don't see the fastest route, you know? I mean, we're all human, and some of these puzzles are tricky. A surefire way to get somewhere is to turn it just into sines and cosines and go from there. All right. All right. Let's just do one more like this or something like it. I'm sorry. Mhm.
This is the basically one way to do it.
Okay. All right. Different problem? Okay. All right. Let's try something a little bit weirder. Let's see.
So I shot right back. I shot back.
Yes, we have done something like this. Start looking at it and thinking to yourself, what does it kind of weird, sort of, kind of look like? What's the, that was a lot of, unknown modifiers in there, but
Oh, is it the?
it's the whatchamacallit, it's near the doohickeys. Yes, exactly. Yeah.
Substitute, so just go for
You know, if you feel like substituting, substitute. If you don't feel like substituting, you're fine with it too. Then it's fine. Yes, this is a like quadratic-esque. Yes. So, stuff a rabbit. All right, so if you feel like making a substitution, go right ahead. I generally like doing substitutions because I'm lazy and don't want to write sine, sine, cosine, sine all the time, especially when I'm dealing with weird stuff to begin with. Okay. So I don't know. I mean, it's just me, but I like looking at that form rather than the sine and the cosine crazy things and things and claws kind of form. All right, so stuff a rabbit. And of course, I'm gonna forget that. Ex- right? Whichever form you like to do. Hmm? And now I can resubstitute. Oops. Be nice if I had a variable in there. Okay. Now, what if, first of all, show of hands. Who got it? That. Okay. Who came close and now sees where they got blockage? Okay. Okay. Now, let's just say I took a problem like this and set it equal to 0. Hmm. Hmm. All right, let's take the same thing and set it equal to 0. Okay? Now, we have two scenarios to fool with. So, equals 0. 2 sine x plus cosine of x equals 0. What am I going to do? Yeah, well, I've got two equations now I got to fool with.
Quickly saying that cost of specific like one. I mean that sine cosine equal 1 third.
All we know is that there are solutions to this problem. Let's see what we can do. All right. And there are values of x that give me a slope of -3. Okay. Um, Not necessarily ones that we see on the unit circle, right? We see square root of 3 and square root of 3 over 3. But that is a solution. There are values for this. And if you really wanted to be specific, you could say, because that's what x is, right? That's what you're looking for. And then you say to yourself, well, cotangent values are not ones that I normally have buried in the back of my brain. So what I'm going to do is I'm going to turn this thing into maybe a tangent or something like that. You should know how to do this. And now, there we are. So now you've seen a technique for solving trig functions, trig equations with quadratic-esque. I mean, like, there were lots of things going on in here, okay? And you can definitely imagine that there might be a problem that could be created where the arctangent of something is on the unit circle. Where, you might have to remember at this point some trig value. I mean, like if I gave you that the tangent of x equaled the square root of 3, you should be able to tell me what x values give me the square root of 3, right? Agreed? Yes, I hope. What is the value of where the tangent is equal to the square root of 3? Come on, unit circle people. Square root of 3.
Pi over 3.
What is a value where the tangent is equal to the square root of 3? Give it to me in radians. Pi over 3 and... I know, I heard you. But there wasn't a consensus. And 4 pi over 3. Right. Okay. All right, since we're back on, guys, since we're back on the unit circle for a moment, okay, there was a problem type that I wanted to show you, and if I can remember where the heck I put my notes. Wait. Okay, here's an example of a problem. All right. So let's think about it. This is not outrageous. So what's the cosine of pi over 6? Square root of 3 over 2. What is the arc sine of square root of 3 over 2? In radians? And think of the unit circle. It's a large y value. It's a large y value, so there are two places where it exists. What are they? Pi over 3 and 2 pi over 3. What about this one? Oh, my fault. Excuse me. It's a negative small slope. Square root of 3 over 3 is a small slope, right? But it's negative. So what does it have to look like? Negative small slope. It's like that, right? 5 pi over 6 and 11 pi over 6. And both of these simplify to what? Right. The cosine is the x value of both of those locations. So you get the positive and negative square root of 3 over 2. Yeah.
The same point cosine pi, that thing is comma inside parentheses.
Yeah. Yeah. This is equivalent to saying they're the same. Yeah. If it was somebody else, well, we don't have values for square root of 3 over 3 with the sines and the cosines, though. Then the problem with saying the tangent of the square root of 3 over 2, or the negative square root of 3 over 2, is that isn't an angle on the unit circle that we're used to, right? Because remember, what does tangent take in? Tangent, sine, and cosine, they take in angles, whereas arc tangent, arc sine, and arc cosine take in a value and spit out an angle, okay? All right, which leads us to another kind of question. Hey,
Sorry,
hey,
I
what's up?
something for you.
Yeah, he's hanging over here. Come on in. Yeah, no problem. And by the way, I'm going to say that theta lives in the third quadrant. So theta, have a go. So theta lives between pi and 3 pi over 2. Okay. Now,
That radius is fine.
so here's what we're going to do. We got to remember what sine, cosine, and tangent are. They are ratios of the sides of a triangle. Okay? Now, the following technique is going to come back and visit us when we start playing around next year with Trig. Okay? Because there are tools that we can use that go back to the original idea of a triangle in order to say, well, you know what? I got some weird looking form. I'm going to go back to the basics, turn it into a triangle, and look at that triangle to find other trig. There are substitutions and simplifications that are going to come back using the following technique. Cosine, go back to SOHCAHTOA. Cosine is what? Yeah, remember SOHCAHTOA. Cosine is adjacent over the hypotenuse. Okay? So first of all, we know that we're living in the third quadrant. Okay? It told us that theta lived in the third quadrant. All right. We don't know yet. We're gonna find it. Theta is in between pi and 3 pi over 2. That's what that's saying. It's saying that's where theta lives. Okay? Well, the adjacent over the hypotenuse. So I have a hypotenuse of 5. And my adjacent, because remember my theta goes like this, right? So if that's my theta right there, if I look at my reference angle on this triangle, I have an adjacent and a hypotenuse. Okay? Now I'm looking for the tangent, and tangent is what? Opposite over adjacent. So I need the opposite side. I already have the adjacent side. It's -4. So how can I get the opposite side? Which is right there. Pythagorean theorem. And what does that yield? Right. That's the 3, 4, 5 Pythagorean triple. Yeah.
If it's negative 3, I articulate I know why the 5 is positive because I have a question.
Because it's a length.
Yeah, so I know. It's like vector.
It is exactly like the vectors. Right.
I kind of feel like
Well, no, that's not entirely true. When I take the square root of a number, I get the positive and negative value. I'm selecting the negative value because the positive value would give me something up here, which I don't want. Remember? So when you do under normal circumstances, regular garden variety geometry that you took a million years ago, we throw away the negative case. We don't care about it. But now we're selecting it because it fits into the problem that we need. Okay? It's the solution we wish. So this is now -3 because like I said, I'm living in the third quadrant. And so now my tangent would be what? 3/4. Okay, that's all wonderful and shiny. But what if you really don't like that? What if you're really not a fan? Okay, there is another way to play the game. Okay, what about this? We know what cosine is. Right? And we have some identities. Yeah. Fluffy, don't misbehave. We know that identity. And we also know that. Those are the two fundamentally important identities that are the bread and butter. I mean, those things are critical. All right? If I didn't have my microphone on, see? Haha. Because I know what cosine is, I can substitute it. See how that works? It's kind of weird, but it's cool. It's just another way of approaching the same problem. Okay? And of course, we can simplify that. That's an ugly looking 5. Now, we have to say to ourselves, which one do I want? Now, we have to remind ourselves that we're living in the third quadrant. If we're living in the third quadrant, is my sign positive or negative? Yes. So I want the negative case. So now, another way to do it. It is longer. But an important piece was made from this. You know that the sine squared plus cosine squared is equal to 1, which means that you can transfer a value from one to the other. You can use these trig identities not just to algebraically manipulate sines and cosines on a page, but you can use it numerically also to find a value of sine or to find a value of cosine or tangent or secant or cosecant, whatever you have. Okay? And it's so what I'm saying is that you can actually, well, first of all, you can use a calculator for crying out loud. Okay? If you guys want to grab a calculator, if you haven't already, don't already have one. So on a calculator, let's go back to the original problem. If you go to the calculator, and if you have the cosine of theta is equal to negative 4/5, okay? So find theta. How do we get theta? Use the arc cosine. Remember, well, first of all, does it matter if you're in degrees or radians? It should not matter.
Oh, because you're not reaching an angle that's on.
Yeah, you don't care, because the angle is irrelevant to me. All I want is the ratio, okay? Whether that angle is expressed in degrees or in radians, it doesn't matter, okay? It's kind of like saying the freezing point of water. It doesn't matter to me whether it's Celsius, Fahrenheit, Kelvin, Rankine, or any of those other ridiculous ones, okay? No one ever uses Rankine except for American engineers, but
What is that?
Rankine is kind of like a hybrid mix between the Fahrenheit and Kelvin scales. Its zero is absolute zero, but the incremental step is a Fahrenheit. Yeah, so you can imagine that engineers who use Fahrenheit would actually find it useful. Yeah, just like in Kelvin. In Kelvin, the zero in Kelvin is absolute zero, right? So go to your calculators, type in second cosine negative 4 divided by 5, hit enter. You're going to get a goofy number, right? Some ugly number. I don't care, right? Now, type in tangent of your answer. So, tangent second answer. What do you get? It gives you negative 3/4, doesn't it? It doesn't give you positive 3/4. Remember the ambiguous case of the law of sines? Do you remember when we talked about the ambiguous case? All right, type in these commands. Second cosine negative 4 divided by 5. And you're going to get a number. What do you do when you get that number? What is that number? Somebody yell it out to me. Okay, now type in tangent, second, and then the answer key, which is the negative sign. What do you get? It's probably going to say negative 0.75, right? Oh yeah, now there's some weird rounding error in there too, right? Because it's doing it numerically. It's not doing it algebraically. So it's going to get some goofy little rounding error in there, right? You're going to see a little bit of mistake. But now, the answer key. Yeah. Now, remember when we did the ambiguous case of the law of sines? For example, if you type in type in the arc sine of 0.9. You're in degrees, right? Yeah, okay. If you think about the unit circle and you realize that the sine values are the y values, If I give you a sine value of 0.9, there's an angle here, and there's an angle here that both give you the same value, right? So take, what did you get, 60-something degrees? 64 degrees? Okay. Type in 180 minus answer. It's okay. Oh, then do pi minus your answer. Okay. And now type in sine of answer. You should get 0.9. 0.89, yeah, rounding error, right? Because there are two sines that produce the same, two angles that when I take the sine of them, produce me the same value, the same height, okay? This is where the ambiguous case comes in. Because if I'm making a triangle with this theta, the question is, which theta is it? Is it the acute or the obtuse? Well, the same thing is happening when we do this same problem we just did here in the calculator. Because when I use the calculator to do this, it assumes that you're living in the second quadrant, that you're living in the upper half of the circle. It assumes an angle here. But that's not the one that we want. Because if you think about this right here as having two x values, two angles that when I take the cosine of them give me the same x value. It's the same idea. Okay? So you need to look very carefully at that so you can decide, well, when I'm done, I get this answer in my calculator that says negative 3/4. But in reality, it should be a positive 3/4 because I want the angle in the third quadrant. And tangents that live in the third quadrant are positive. Okay? So in a sense, this is an ambiguity in cosine because you have two cosines. Okay? It's the same idea. The ambiguous case can be tricky. So calculators lie. And you have to use good judgment when you look for a numeric answer. Ask yourself, is this what I really want? Because calculators don't know which one you want. You can't load into the calculator in advance, oh, please only give me values in the third quadrant. You know, it doesn't work like that. All right. So, let's try this. Find me the So start by drawing a circle, a coordinate grid. Decide where you're living. Where am I living? What quadrant am I living in?
Isn't it the other way around?
Hold on.
Make the smaller value less than...
Hmm?
Shouldn't it be the smaller value first?
It's, yes, sorry, brain damage. Hey, that's my goof for the day, you know? Hey, as goofs go, it's not the end of the world. I'm living in the second quadrant. I'm less than pi, but greater than pi over 2. Yeah. Huh? What? I'm sorry?
Like tangent, it's mean, like using you know, like things of X equals R, and like Y equals R, that stuff.
Yeah, okay, right.
I use that.
Try it. Okay, so I'm living in the second quadrant, so whatever my triangle actually looks like, it's going to have this general shape, okay? Remember, we're always dealing with a reference triangle. We want to go to the x-axis as fast as possible. So if this is my, if the tangent is equal to the opposite over the adjacent, well, if my opposite is -5, wouldn't I be going down? Right? According to this, it almost looks like I should be living in what quadrant? Yeah, it doesn't quite fly. In fact, if it was instead here, that would give me the same tangent, wouldn't it? The question is, which one do I want? Both of those angles give me the same tangent. I want the one in the second quadrant, not the one in red. Okay? So this is how I'm arranged. And using the Pythagorean theorem, and I'm going to save us all the trouble, what is my hypotenuse? Thank you. So now my secant is 1 over cosine. Cosine is adjacent, well, opposite over adjacent. Sorry, no, adjacent over hypotenuse. So now I want hypotenuse over adjacent. Right? And if you confirmed it with the calculator, you should get 1 and 1/12. Okay? 1.083 bar, right? Okay, great. Last one of this type, and who? What?
Okay, so you figure out what quadrant it's in. You don't even, do you really even need to solve the triangle? Because,
Not always, but in this case, you might. The one I'm about to give you.
oh goodness.
Well, the problem of that style, no, you can use your identities and your logic to determine what the answer will be. In the example I'm going to give you right now, you really should draw a triangle. Take a second to copy this down. This is a great problem. I like this one very much. Okay, you got some weird, goofy word problem. Best advice always, draw a picture. Over 3, down 1. That's where I am. Roughly, right? Okay? Roughly speaking, that's where I am. So that means I'm dealing with this. There really isn't very much trig involved in this at all, except the identities. So now I want cosecant. Cosecant is the reciprocal of sine, which means I'm going to need a hypotenuse in there somewhere, right? Okay. So let's find the hypotenuse, the length of my hypotenuse. Pythagorean theorem. It's 3.16 and change. And the cosecant is the reciprocal of sine. And the sine in this case is, well, sine is opposite over hypotenuse. So this is hypotenuse over opposite. No, not really. Especially after you draw a picture. Okay? And if you go to the calculator, really what we're saying here is that the tangent of this angle is negative 1/3. Rise over run. Take a message, I'm not here. Oh, okay. Yeah, take a message. It's okay. All right. Now, there is another problem set that I will post of trig identities. If you are falling behind on these, please knuckle down and start doing some of them. There's only like 6 or 8 problems on each of these identity sets that I'm going to give out. I'm going to be giving them out on a regular basis. Okay. Next class, you got one due to me. 6 problems. Okay. All right. This episode of the Ronco Show has been brought to you by our friends at Coterminal Angles and sine, cosine, and tangent.